My topic is nuclear fusion. And nuclear fusion, I'm first going to explain it in very simple terms. And in very simple terms, nuclear fusion is the merging together of two separate atomic nuclei into a single atomic nucleus. And before I get into the specifics of nuclear fusion and how this merging together occurs, it's essential for us to first understand the forces which act upon the atomic nucleus. And we have two forces here. One of those forces is the Coulomb force, and the other one is the nuclear force. Now, the Coulomb force is easier for us to understand because we already know what it is. It is the electric attraction or the electric repulsion force between two charged particles or two charged objects. So we have a proton and another proton. They repel each other because they have the same charge. And we have, say, an electron and a proton, and they attract each other because they have opposite charges. So that's the Coulomb force. And then we have the nuclear force, which is a new concept to us, but it's again easy to understand because it's essentially the neutron, the attraction force between a proton and a neutron. So inside the atomic nucleus we have both Coulomb forces and we have nuclear forces. So we have proton-proton repulsion and proton-neutron attraction. Now, one thing of note about these two forces is that the nuclear force generally tends to be stronger and the Coulomb force generally tends to be weaker, while the Coulomb force has a longer range of effect, while the nuclear force has a shorter range of effect. And this is why we require a lot of energy during nuclear fusion. We first have to overcome the long-range Coulomb forces and bring the atom as close as possible so that the nuclear forces will come into effect and bind it together. Now, here's an image, so the whole process of nuclear fusion will be easier for us to understand. As you can see here, we have two separate atomic nuclei, and we have the Coulomb force and the nuclear force in effect. And we can see that the Coulomb force has a longer range of effect and the nuclear force has a shorter range of effect. So, in order to put nuclear force into effect, we have to bring the two atomic nuclei closer together. And we do that through energy or pressure. So, we give the atomic nuclei energy, and then we bring it closer and closer and closer and closer and closer together, till the nuclear forces come into effect. And when those nuclear forces come into effect, the atomic nuclei are bound together into a single atomic nucleus. And we have a large outcome of energy. And this outcome of energy is entirely dependent on Einstein's most famous equation, which is E equals mc squared. The E being energy, m being mass, and c being the speed of light, which is 300,000 kilometers per second. Now, what this equation essentially states to us is that any amount of mass can be turned into energy. And this is the basic principle of nuclear fusion. Because during nuclear fusion, we actually observe that some of the mass has been lost. So, for example, say that we have two separate atomic nuclei, and they each have a mass of 1. So we have one on this side and one on this side. And together they make a total mass of 2. And we fuse them together, and then we look at the resultant larger atomic nucleus, which is supposed to have a mass of 2. But it does not have a mass of 2, it has a mass of 1.9. So that 0.1 has been lost, and that loss of 0.1 has been converted into energy. And this is the basic principle of nuclear fusion. This is how we gain energy from nuclear fusion. And now that we've looked at the outcome and the process of nuclear fusion, the next question is, where does nuclear fusion happen? And the most natural answer to that, and the easiest answer to that, is the stars. Now, here is a very bad image of a star. And there is one thing we know, is that stars are massive stellar objects. And because they are massive stellar objects, they also have massive gravitational forces. So, every single particle or object surrounding the star will be attracted towards the star. And also, every single object or particle in the outer layers of the star will be attracted towards the inner layers of the star, because every stellar object exerts all of its gravitational force from the center of gravity. So, we have particles and objects in the outer layer trying to make their way into the inner layers. And we also have particles in the inner layer being subjected to a massive amount of pressure, because these particles are trying to make their way into the inner layers. So the particles at the inner layers will be subjected to an extremely high amount of pressure, and their nuclei will be forced together, and we will have nuclear fusion within their centers. Now, besides stars, there is also another product, a man-made product, which does nuclear fusion, and it's called a thermonuclear bomb, otherwise known as a hydrogen bomb. And what this bomb essentially does is, it first does nuclear fission, and the energy produced from that nuclear fission then is used up to make nuclear fusion. So, nuclear fission gives us energy, and that energy is used to make nuclear fusion happen. And this is the only case in which we have done nuclear fusion successfully. So if there's a question of what does nuclear fusion, the two answers could be a star and a thermonuclear bomb. Now, nuclear fusion really is an efficient way of making energy. Even though we require a lot of energy and a lot of pressure to bring those two atomic nuclei together, the net energy produced from nuclear fusion is higher than the amount of energy that we use. So we will always have a net gain of energy, and we will always have a massive amount of net gain energy. So nuclear fusion, if we can unlock its secrets, could give us a way of producing massive amounts of energy and potentially solving every energy problem in the world.